So obviously, Dr. David Westcott, who's been the PI for the Integrated Pest Management Program over the course of its last 5 or 6 years, will talk mainly about the what of what has been achieved. But we also think it's important to document the how. So how has this extraordinary improvement in defending live coral cover on the GBR been achieved? We find quite a lot of the case studies we're writing for our synthesis products are concerned with the process, with the how, and we think that's potentially important lessons learned in how to design environmental research programs for impact. So I'll just talk for about 5 minutes, and then Dave Westcott will talk about the what that's been achieved. So essentially, IPM aims to deliver the most efficient and effective control of the pest, and in this instance, live coral cover saved, for the available resources. And importantly, it also enables control programs to evolve in effectiveness as new knowledge and tools become available. So in designing the COTS Integrated Pest Management Strategy, it was important to have a very strong focus on what was going to improve the effectiveness of the control program. We had to overcome a lot of really entrenched divides across disciplines and institutes, from managers to practitioners and the scientists as well. So what I'm sharing, that I hope you can see on my screen, is not for distribution, please. It is a diagram that attempts to convey the complexity of what has been involved in the NESP COTS Integrated Pest Management Strategy. The process of putting together this strategy drew across a broad range of experience, and that's really important, from managers with policy backgrounds to managers and practitioners with on-water control experience and activity, and from Australia's COTS research community, as well as researchers with experience in designing successful integrated pest management strategies. So everyone can now see this horrendously complicated COTS Integrated Pest Management Strategy that was put together across multidisciplinary and institution boundaries. And this is how it actually rolled out in process. I'm obviously not expecting you to try to read any of this. I just want you to see how it was integrated, a strategic process that rolled out over time. The success of it was principally because of the collaborative approach that was taken, the leadership shown by David Westcott over time, and the ability to integrate information from a whole bunch of different areas such that there would be impact on the COTS control program. So before I lose everyone with this complexity, once the research strategy was put together, teams of researchers with appropriate expertise fulfilling these research needs were identified and harnessed to deliver information in line with the research needs identified in the strategy. Importantly, the NESP Tropical Water Quality Hub had the ability to commission projects in stages as we went through the 5 years, rather than fixing the research program from the beginning, which meant that the program could be responsive over time. And you can see the 5 years of the research strategy rolling out at the top of the screen. That was really important to achieving impact, and also the capacity of the RRRC as the sort of pivotal organisation to provide that important link between the research programs being conducted within the NESP and the actual on-water control programs being conducted through AMPTO and more recently GBRMPA and GBRUF and INLOC. So maintaining productive three-way relationships between all these organisations was really important. So that doesn't seem to be anything there. I'll just finish there and let Dave Westcott talk about the what was achieved. But I think it's really important for people looking to design applied integrated research programs for impact, understand what some of the successful characteristics of those projects are. Okay, I'll somehow hand over. Stop sharing.
Thank you, Suzanne, for that introduction. And I'll get David now to begin sharing his screen, and we'll go from there.
All right, I have unmuted myself. Can you hear me there?
Yes, we can, David.
You can? Excellent. So good morning, everyone, and thanks for tuning in to listen. So in my usual style, I've forgotten that I actually gave a title to Julie when she was organising this, and so when I came to prepare my slides, I have a different title to the one that I was said I would talk to. It's the same talk though, and I'm going to cover the work that we've done right throughout the 5 years of the NESP program, and I'm going to talk about contributions that come from a range of different institutions, and I can't get this to progress. Okay. A whole range of institutions that were contributing to the contributed to the research, and a whole range of people from each of those institutions. I've underlined the names of some of the people who played particularly important roles in some of the institutions there, but you know, I'm going to talk a lot about we, and collectively this is who we is. I'm going to try and cover a whole lot of ground in the talk today, and so just give you a bit of an outline so that you can track us as we move through the talk. But first up, I'm not going to assume that everybody's familiar with COTS, or Crown-of-thorns starfish, and so I'm going to give you a brief introduction to COTS outbreaks. I'm then going to talk a little bit about the approach that we used to develop the IPM strategy. Suzanne's given you a quick overview of some of that. I'm going to talk to some of the details around how we did that. And then I'm going to launch into talking about the research that was conducted. Now, in the first instance, I'll talk about some of the supporting research that was funded under the program, but the majority of the talk is going to focus, in the first case, on the control program itself, and you know, how the design translated into the action that's taken on water. So I'll talk about how we actually go about control and why we've chosen particular technologies. I'll talk about how we then apply that control method to managing a site, and then the decision processes in particular about how we scale that up to achieve control at much larger spatial scales. I'll then say, well, that's nice. How well has the program performed? And I'll just give you some details on that. And I'll compare it to the previous approaches that we've used in controlling Crown-of-thorns. And then I'll wrap up by thinking about what the potential for control of future outbreaks is under an IPM program, and what some of the constraints on the scale of that or magnitude of that success might be, just before wrapping up. So first up, the problem with COTS. Well, essentially COTS are predatory on coral, and they consume the hard corals that are the structure, you know, that build the structure of reefs, the structure and the complexity, and allow the complexity of reefs. So COTS in themselves are really attacking the fundamental component of coral reef structure, coral reef condition. Now, in a seminal paper back in 2012, Glenn Diath and his colleagues at AIMS estimated from the AIMS long-term monitoring plots that there'd been approximately a 50% decline in coral cover over the previous, whatever that is, 25 years. And they were able to assign the blame or the causes of mortality to three major causes. They were cyclones, Crown-of-thorns and bleaching. And at that time, cyclones had been the most important. COTS ranked second, bleaching third. Of course, you know, as conditions vary through time, we'd expect those rankings to shift around, and we'd probably say that bleaching is now, you know, the dominant cause of coral mortality, with perhaps COTS running second. Cyclones are distant third. Irrespective, COTS were then and remain today and will remain into the future a major cause of coral mortality. And so if we want to manage the health of the GBR into the future, managing COTS becomes really an important focus, because COTS are something that we can actually manage. We can't manage cyclones and coral bleaching at the scale of the GBR, but we can manage COTS. So how do COTS outbreaks occur? What drives them? Essentially, what we've seen on the Great Barrier Reef is 4 outbreaks at roughly 15-year intervals, and starting in 1962, and we're well into 10 years into the second major outbreak on the GBR. Now, at any given point on the reef, when an outbreak passes over that site, what we can see is up to as much as 90% coral loss. So it's really significant impact on the reef. And the way these outbreaks occur is that they appear to begin in an area that we call the initiation box. And I don't know that if you can see my pointer, but anyway, here, it's in the area between Cairns and Lizard Island. We seem to get a buildup of adults that produce mass spawning events, and then those spawning events then propagate as like a wave, running down the reef over the years, running south along the currents, and we think potentially also running north, so we don't actually have any particularly good data on that. Those are the outbreaks on the main GBR. That's the pattern and the process on the main GBR. There also appears to be a sort of continual outbreak that happens down in the Swains. I'll conveniently sort of ignore that for most of the rest of this talk, but pretty much everything I have to say will apply to that outbreak as well as to the main outbreak on the GBR. There are a whole range of hypotheses for what causes outbreaks, but I think at the very core of the outbreaks is the fact that these animals have enormous reproductive potential. Individual females can produce tens of millions of eggs, and so they have an inherent capacity for rapid increases in population size. But hypotheses for other drivers of these outbreaks are the loss of predators, in particular triton and large predatory fish, increased or deteriorating water quality inputs into the GBR, providing more nutrients and improving recruitment, and then combinations of climate effects, currents, water temperature. So we don't actually know which of these is the most important. I suspect that it's actually going to be a combination of a range of these different things. So at this stage of the game, it's a bit of a moot point. So the approach that we have used, that's why we want to manage COTS, but the approach that what we were asked to do when we set up the IPM project was to design a research strategy that would support the management of COTS on the GBR. And when we started talking to managers, to researchers, and to the vessel operators, we found pretty quickly that there were really 2 quite distinct camps. There was one group, largely comprised of researchers, if we're honest, that said, we can't do anything about this outbreak. We should focus on research to understand COTS and why they outbreak, and new control methodologies so that we're ready for the next outbreak. Another camp was saying, we have an outbreak, we can use this as an opportunity to learn how to implement COTS control, and that would require focusing on existing tools and developing up strategies that assist the management on water. Now, we decided to choose the second approach for a number of reasons, and one of them was, we have an outbreak. This is an opportunity to actually learn how to go about doing control. But the other was that a lot of the cause of outbreaks is definitely interesting and it's definitely of relevance to how you go about managing COTS, but it wasn't clear that there were any direct levers that research would actually provide us for managing COTS themselves, and management was the imperative. So we decided to go with that second approach, and we broadened out the task that we had at hand, and that was we developed a control strategy and an approach to implementing control on water. We developed up the ideas of how you go about implementing that and identified the research to support it. That was all pulled together in this initial report that came out in 2016, I think it was. And to develop up that whole approach, we brought together all of operators, managers, researchers. We regularly had 30 people sitting in a room, hotly debating what a control program's objectives should be, what the important processes were, and what the logistical constraints were. We then went away and formalized that into a management process, and we took that back to the operators in particular and to the managers and let them live test that process. And then went back and started identifying what the limitations were, what would prevent the implementation of that process. That started to tell us what the research needs were and allowed us to associate that, to develop that associated research strategy to support the work. One of the things that was really clear from the outset, it didn't matter who we talked to, whether it was operators, on-water operators, managers, or researchers. What was really lacking in the COTS control program was a clearly defined, achievable objective. Everybody had ideas about what the objectives were, and they ranged from the really simple, let's just get out there and kill COTS, let's kill, all the way through to we need to eliminate COTS from the entire GBR. But when you pressed people, they really couldn't put into, aside from those sort of general terms, they really couldn't say, this is the objective and this is how we'll know we've got to it. Now, so having an objective is absolutely fundamental to success. And at the time, we decided that having a clear objective was really important. But the real hurdle was that we weren't really sure about how effective our tools were and how far we'd be able to scale them up. And so what we did was we chose an objective that was implicit in the existing program, and decided that provided us with a starting point, and that was that we would attempt to reduce COTS densities to zero, or as close as we could get to zero, at particular management sites, defined geographic sites on a reef, and potentially go to much harder objectives, or increase the difficulty and the ambition of our objectives by expanding that once we understood how well the different tools worked. So defining that objective at the outset was really an important thing. We then had to say, well, there are a whole range of different scales at which management can occur. And at each of those scales, we need to identify what the reasonable objectives are, and we need to identify the decisions that managers need to make and the actions they need to take. From that, we can identify the hurdles that they face and the opportunities for research to actually improve management. And so we know that dive or culling operations happen at a site, so that's a natural minimum unit, a spatial unit, and we need a set of strategies that will enable divers and managers to effectively manage at a site. And so that implies that there's going to be some research around how best to cull at a site. And you have similar sorts of processes that go on at each of the different levels. The next scale up from sites would be reefs, entire reefs, and then the next scale up from that would be regions. And if you can manage at those scales, then potentially at a regional scale, then potentially you can start to think about how you might manage, for example, the initiation box, and how you might control a new outbreak or prevent a new outbreak, or how you might control the spread of an existing outbreak. So at each of those spatial scales, all the way up to the GBR, we thought about the management decisions that were required there and what stopped us from being able to make those decisions or take those actions, and the research that that implied. And that was the research that we set about focusing on. Now, as Suzanne indicated, this very quickly gets very complex, and there's a whole lot of different research that we could do. And so what we really had to do was focus down. It wasn't sufficient for research to be interesting or for it to be relevant to control. We were looking for research that filled particular gaps in our capability, and we had to be able to identify where and how that research was going to be used and by whom. It had to map into a particular tool or a particular decision process. And also, there was no point us doing research that was contributing to something that might become available 10 years down the track. We needed to do research that was focusing on things that would help us in the time frame of developing up our IPM. So that was the general approach that we took. And first up, what I'd like to do is just cover off on some, in talking about the research, I'm just going to cover off on some of the supporting work that we did, just to give you an idea of the variety of smaller contributing projects that were part of this work. So for example, one of the initial real points of contention amongst the group that we brought together was the importance of deep reefs. There was real concern that COTS control was really only focusing on the top 15 meters of the reef. And there's a lot of reef that goes deeper than that, much, much deeper than manual or divers can go. And we know there are COTS on that reef. Were we in fact sort of literally just skimming off the COTS on the top, rather than, and were we missing what might be the significant part of the problem or a significant contributor to outbreaks in the deeper water? To answer that question, we needed to know, A, how much deep water habitat there actually was. That information wasn't available. And how many COTS were there. We did the first part as a modelling exercise, and Rob Beeman from JCU modelled not only what proportion of reefs is in deep areas, but used geomorphological modelling to predict how much coral habitat or potential COTS habitat was in those deep water habitats. And he found that significant proportions, up to 92% of reef area might be below 15 meters, and significant areas of coral habitat could be found at these reefs on the order of 5 to 52%. But going through the literature, the deep reef literature and research that was available, he was able to find very little evidence of high COTS densities. So that bit of work allowed us to park that concern. It didn't wipe it out, because we have subsequent evidence that suggested that we may need to have some focus in deep water, but it allowed us to say, for the moment, the deep water COTS are not driving these outbreaks. Another key area of work that a number of institutions were involved in was looking at the role of predators in managing COTS or influencing COTS dynamics. Loss of predators has been identified as a potential cause of outbreaks, and we know that it's supplementing or augmenting predator populations or conserving predator populations through zoning are potential tools in a control toolbox. And so we had researchers from AIMS and from JCU investigating, trying to identify which are key predators on the different life history stages of crown-of-thorns starfish. And they've identified a full suite of different species for each of these life history stages. And then looking at the influence of zoning, and then some additional work looking at the potential for using something like Triton as a control agents. And I'll talk a bit more to both of those issues further into this talk, but there are a whole range of papers and reports have come out on looking in this particular area. Those are just a couple of snapshots to give you an idea of the kinds of additional work that was being done, but it covered everything from COTS behavior, movement, through to modeling of population dynamics, identifying appropriate COTS habitat, developing monitoring technologies, looking at the social and economic benefits of control, and thinking about management strategies more broadly. A whole range of the reports and journal papers that have come out of this work are available on the Tropical NESP, Tropical Water Quality Hub website. I won't talk any more to them right now, though. because I want to focus the majority of this on talking about the control research and the control program that came from that. So again, when we started, there was an enormous amount of debate and disagreement about what was the most effective way to actually cull or control COTS populations. One camp suggested that we needed to focus our efforts on water quality improvement. Others suggested that focusing on zoning was important, while others, in particular the control operators, swore black and blue that manual control was the way to go. Given that these were the three management options we had available, we looked into the effectiveness, did some analysis of the effectiveness of each of these, as demonstrated by results from the field. And this came out in a report and then more recently in a paper that was published earlier this year. Now, the three: water quality improvement, zoning, and manual control. When we looked hard at these, what we found was that water quality improvement efforts have received an enormous amount of investment and effort over the last 20 odd years, but appear to have resulted in fairly negligible changes in water quality over time. Small enough that it's pretty, and in fact, undetectable changes when you get out into the reef, onto the reef proper. That suggests that they've probably had negligible impacts on Crown-of-thorns population dynamics. And that's reinforced by the fact that we had an outbreak initiate and begin right in the middle of the period that we're considering here. So our conclusion from this is essentially that while water quality improvement efforts are likely to be really important for a whole range of other reasons, at least at this stage of the game, then we can't see that they're effective or a reliable approach to COTS management today. We looked at zoning, and one of the things, this work that was done by AIMS and also by us at CSIRO, and what we've identified out of that work is, you can see in the top plot on the right here, that in different zoning areas where you have take and no take, commercial and recreational fisheries, limited take, which is just recreational fisheries, and no take zones, they have a real influence on the COTS densities that are observed at the outset of an outbreak. So much lower densities at sites that have more restricted fishing opportunities. So zoning actually reduces the densities of COTS, but it doesn't actually stop a COTS outbreak from forming on a particular site. It does, however, improve the resilience of that site, and so the impact of a COTS outbreak appears to be lower at a no-take, an area that's zoned as no-take. So it suggests that zoning is an effective management tool, but it's not effective in preventing an outbreak at a site, just in reducing impacts. Manual control, on the other hand, was found to be really very effective. Excuse me. Our data says that manual control reduced COTS densities to below critical thresholds at sites, and as you can see in the plot on the right, allows for coral, if you manage, there's a positive relationship between the amount of management you invest at a site and the change in coral cover that you see at that site. It's a very messy relationship, which is not surprising because during the period that we saw that this analysis covers, we had two major bleaching events. So there's a lot of other factors influencing coral mortality during the period we're doing this analysis, but still there was a strong and significant signal of COTS control. So manual control, on the basis of our assessment then, manual control is effective. Zoning makes a real contribution, and they have to be important components of our COTS control toolbox. In more recent work, we've also looked at potential future technologies, silver bullets. Are there other things out there that we're not currently using that might actually end up being really, really helpful? We reviewed 4 different kinds of technology, biological control technologies, using predators and, as I've already outlined, using microbial and viral agents, essentially using diseases, using the signaling COTS, essentially you can think of it as COTS pheromones that signal particular reproductive processes, using those to, taking advantage of those to improve the performance of manual control. And then using some of the new gene technologies, CRISPR and Cas9 technologies to edit COTS genomes for biocontrol outcomes. The assessment of these things is that there is some real promise, and all of these areas are worthy of further investigation. However, only one of them, and that is the predator conservation, has really immediate potential. Pretty much all of these approaches face really significant scientific, technological, regulatory or ethical hurdles. And the consequence of that is, and if you look on the plot or the figure on the right-hand side here, if we look at the timeline going through to the next outbreak, which is probably going to start somewhere between now and 2025, and is shown in white on that timeline there, below that you can see in green when these different technologies might actually start to become available. And really, even the most short, the most the technologies with the most rapid development potential are probably not going to be available until well into the next outbreak. And a number of them are probably in reality not going to be available until into the outbreak following that. So that really leaves us focused on manual control and predator conservation. And I should also note that some of these newer technologies, even if we do develop them up, they will still be dependent on some degree of manual control to improve their efficiency. So manual control is going to remain central. Sadly, there's no silver bullet that's about to become available to us. And so we need to make sure that we can do manual control really, really effectively. So we know how to employ manual control to kill the animals, but we then have to deploy that effectively to achieve control at a particular site. And so a large amount of, a significant focus of what we've done is been developing the strategies that ensure that we manage sites down to below key particular thresholds. And so there's been a range of work involved in that. Identifying the thresholds, when to start management and when to stop management, has been a really important step. And that comes from work that was done by Russ Babcock and Yves Blagagne and Jacob Rogers at CSIRO. And they've identified two sets of thresholds that we use in the program. The first of these is an ecological threshold. And so they've used their modeling approaches to estimate the density of COTS that can be sustained before you start losing coral cover to COTS predation. Of course, this is a function of the amount of coral cover at a site, but we can choose a minimum density of COTS of approximately 5 COTS per hectare. As soon as it goes above that, that minimum threshold or conservative threshold, we can expect to start seeing coral loss. So that's one threshold that is focused on protecting coral cover at the site. But there's also another threshold, a reproductive threshold, where if COTS density goes above that threshold, their fertilization success begins to improve rapidly. And so essentially COTS are broadcast spawners. The closer they are together, the more likely that sperm and eggs will meet in the water column. And so the greater the fertilization success. And so based on the modeling that this team has done, they've identified a threshold of about 3 COTS per hectare as the reproductive threshold. And that's not protecting coral at the site. What that's doing is protecting the downstream areas from, reducing COTS dynamics at downstream areas. So in all of the stuff that I talk about today, I'm going to use this minimum threshold of 3 COTS per hectare as the target threshold. And it's just worth noting that in the COTS program, we regularly achieve well below that threshold at sites. In fact, on average, we're achieving 2 COTS per hectare at sites. Now, we have done a whole range of other work which is somewhat more mundane but important. Things like identifying the importance of coming back to sites on a repeated basis and working out what are appropriate intervals for returning to manage control at a site. These are all small pieces of work that actually have really significant impacts on the outcomes of control at a site and the amount of coral that has been covered, that is saved from COTS predation. So we know, if we know how to control COTS and we know how to cull the animals and we know how to implement that at a site, how can we then go about scaling up that process to much larger areas, to reefs and to regions? This is functionally a process of identifying a decision process, how we distribute our effort across reefs. And we've outlined this in a report that was published at the beginning of this year. And there are two levels to this. First, we have to make a decision about at which reefs we're going to invest in control. And then we have to make decisions about how we're going to distribute our effort between those reefs and across all of the sites at those reefs. And I'll talk to those two steps separately. So the first is this decision: how do you decide which are the reefs you're going to manage at? You can't manage every reef, we don't have the resources. Working with Gurrumpa, we identified a process that allowed us to, that essentially worked by assigning a value to a score to a reef. It's perceived value on the basis of a range of potential values. They might be economic, cultural values, they might be coral cover or the density of COTS at a site, and importantly, they might also be connectivity of that reef to other reefs on the GBR. And that's important if you're thinking about the dynamics of COTS outbreaks or of coral recruitment processes. It's a simple process. Works on a spreadsheet. It's been run and is now being run by Gurrumpa as part of their decision, or it's been refined and is used by Gurrumpa on an annual and semi-annual basis in deciding what their priority reefs are. And a key component of developing this up has been the connectivity modelling that was done as part of the NESP program by UQ and CSIRO. The second component then is we know which reefs we want to manage at. How do we then go about sending boats out to those reefs and to particular sites on those reefs? And as part of this, Mary Bonnen from Gurrumpa, Cameron Fletcher and myself have developed up a decision support tool or a decision tree that actually goes through every decision that vessels have to make from the time they leave port to go out and do their control. It, identifies the status of a reef and then says, well, given this status, when was it last visited? What are the tasks that have to be done here? And steps all through every single decision the vessel has to make before it returns back to the port. This decision process operates on the idea that we aren't just managing sites, we're managing reefs in their entirety, and we manage reefs until we achieve our sites and reefs until we achieve our objectives, which are pushing them down to below the thresholds, the reproductive threshold, and only then do we start working on other reefs. And that's to prevent us from spreading our resources too thinly. Overall, the design of this tries to balance out our understanding of COTS ecology and biology with the logistics of vessel operations. And it balances out those things in an attempt to make sure that we achieve control program objectives. And this wasn't something that we just developed up in one hit. It involved a cycle of discussions, design, laugh testing that design with vessel operators and with managers, going back, refining it, laugh testing that design again, and field testing it until eventually we had a process that worked. And that's a process now that has been guiding the program. Our IPM program's been operating on, the control program's been operating under this process in an analog version since late 2018. We are very shortly going to be running this out as a digital version as well. And the reason for doing that is that this process, and as an analog process, there's a big delay in getting data into into the decision process and being able to action that decisions based on that data. And it means that vessel operators are sometimes not able to make decisions based on the day and based on what they're actually seeing on the water. So this new app will be a COTS control center, and it'll allow, these are just screen grabs from the app, allow operators to say, well, this is the area of the reef that I'm working on. These are the reefs that will be visiting on this voyage, and this is the reef that is the highest ranked priority. It'll then say, well, at this reef, for example, Britomart Reef, this is the recent history of what's happened here. This is when it was last culled. This is when it was last mantatoed. This means that actually one of the first tasks has to be to mantatoe it again. It'll allow the operators to look and see where mantatoes occurred in the last voyage, and it'll allow them to identify, in this slide, it'll show where high densities of COTS, which particular sites had high densities of COTS, and you can see high densities are shown in red and yellow and green on this. So it'll give it a recent history of a site. It'll then refer back to the decision tree to say, according to the decision tree, the first task you have to do here is a mantatoe. It'll then take the vessel operator to Gubrumpa's mantatoe data entry portal or app and allow them to go ahead and conduct those mantatoes. It'll then suck that data up and say, well, based on the data that you collected this morning, these are the parts of the reef that have high COTS densities, and these are the particular sites that have densities above the thresholds, and you should manage them in this particular ranking. Site number 1 has the highest density, site number 2, site number 3. That's what your work plan looks like for this particular reef. So the value of this is that it makes the decision process consistent across all of the operators, and it allows them to make their decisions in real time based on the data that they collected this morning or that another vessel collected on reefs further down the GBR, because the app is actually sucking in data from all of the vessels and from all of the Gubrumpa databases to inform these decision processes. We expect to see that being available in the next few weeks. So that's the program. How well has it performed? As I said, we've been operating, the entire fleet's been operating under IPM rules since November 2018. We did have 6 vessels, but 1 dropped out after not contributing a great deal to the program. So we're now of 5 vessels. We've achieved about 1,200 operational days across those vessels. That equates to roughly 50% of the time, 50% of days have cull activities or mantatoes conducted on them. The remaining days are weekends, holidays, transit time, training, vessel maintenance, that sort of thing. So that's a pretty good outcome. Since November 2018 to July 2020, the fleet conducted operations at 202 reefs. They conducted surveillance around the entire perimeter of all of those reefs. That's about 8,400 kilometres of mantatoes. 81 of those reefs were identified as requiring no cull because no COTS were seen in the mantatoes. 103 required culls, and since in the time frame that I'm looking at, up to July 2020, 92 of those 103 reefs had been managed to below our reproductive threshold of 3 COTS per hectare. The remaining 18 reefs were scheduled for culling. So, was the culling effective in reducing COTS numbers? Well, I've already alluded to that, but yes, what we're seeing in this plot on the right is the median number of COTS that were culled on the first, second, and so on voyage up to the maximum number of voyages to individual sites, which was 21. Now, it's really important in this to note that this data refers only to sites that remain in intensive management mode. So this line above the box plots that you see shows that as sites are managed, they're removed from this analysis. So we're really just looking at the worst sites in the control program, because by the time you get down to roughly 6 or 7 visits, you're down to a quarter of the 884 sites that you originally started at. So this is the worst case scenario, and the worst case scenario is actually looking very good. Within 2 voyages, we've pushed the median density at sites remaining at remaining under control to below our reproductive threshold. And by 6 or 7 sites, we've got it down to 75% of sites. We do have to keep going back to some sites. Some sites require long-term ongoing management. And one of the real questions and why we keep going back to these sites is to try and understand what it is about them that means they're so difficult. Across all of the sites, whether we achieved our threshold or not in the analysis time period that I'm looking at, the mean final density in July 2020 of those sites was 2 COTS per hectare. So that's well below the threshold that we're seeking to achieve. So that's really encouraging. As I said, we managed approximately 884 sites. Most of those sites required only 1 visit to assure ourselves that they were down below the threshold. Sites that were above the threshold required on average about 6.7 voyages, whereas for reefs, we had a similar story for reefs. Reefs, more than 70% of reefs were visited just once, but of the reefs that needed to be visited more often than that, we're looking at roughly 14.5 voyages to the reef to be able to push that down to the entire perimeter to below the threshold. So that requires a significant investment in time, but under the program, voyagers should revisit sites and reefs on roughly a 10-day period. So we're looking at essentially a couple of months for a site and up to 6 months for a reef on average. A critical question is, are the rules that we're using to make decisions about control reliable? There are a whole number of these, but the critical one that we want to look at is whether the decision to dive a reef is reliable. We want to estimate, and that decision is based on mantatoes, whether you see 1 or more COTS, individual COTS, or 1 or more feeding scars. If you see 1 of either of those, then you should dive the site. That's our rule. And because we have chosen to dive a number of reefs and a number of sites where we saw no COTS or scars and mantatoes, we're able to assess the efficacy of that decision rule. And we're able to say, we're able to make 2 types of mistakes. One is to dive when we don't need to. And what we find is that 97% of the time we will, if we choose to dive without seeing any COTS or scars, we will find that we don't need to dive that site. The other mistake we can make is not diving when we need to dive. And there's only a 3% chance based on the data we have to hand at the moment of making that mistake. So that decision rule, the really fundamentally important one, it's not perfect, but it is fit for purpose and has a small chance of making the bad mistake that we don't want to make. So that's a bit of information about the program, but we should ask, has it actually improved our performance? What we're able to do is look at the different phases of the COTS control program. We're really lucky that the initial program that ran from 2013 to 2015 collected a lot of data on their activities. They did a really good job of this. So we're able to use data from that phase to compare it to the data that we have from our current phase. But it's just worth pointing out that that pre-IPM phase, as I'll call it, operated under the similar decision rule around culling individuals. They tried to cull as many individuals as they possibly could. And they claimed to have a focus on 21 reefs, but a critical point is that they were highly reactive. And so that focus kind of dissipated over time when they got reports of very high densities of COTS at other locations. So ultimately, they managed 260 additional sites at another 81 reefs, and spent a lot of time not finishing the job, but rushing off and managing somewhere else. There's a period 2015 to 2018 where we gradually started introducing IPM rules, and then we have the period where we were focused on program objectives and the IPM rules were adopted across the entire fleet. Now, this is a comparison of the performance of the pre-IPM and the IPM phase. It's a bit of an eyeful, but we'll go through it slowly. So on the left-hand column, I have a range of performance metrics. The second and third columns are the performance against those metrics of the two phases of the program, an assessment of which actually perform better against those metrics. And then sort of I've identified the scale of the objective, and that's, is it an objective at the cull level, site level, or reef level? And it's worth remembering that at the cull level, this is a functionally how well can we kill animals? It's the easy thing, and it's actually not really what we're trying to achieve. We're trying to kill smart. And so we want to see good performance against the site and reef level. Well, the pre-IPM program was really effective at finding sites with high densities of COTS, roughly 3 times the density that we found in the IPM. They killed approximately 50% more COTS. They did so at roughly twice the rate in terms of COTS killed per operational day. So they were very good at killing COTS, but at sites where they reduced control densities to below the threshold, they performed at roughly the same rate as the IPM program. If we move up and look at how quickly they were able to reduce COTS densities at a site to below the threshold, we find they didn't perform as well as the IPM program. They took 2.5 times as long to cull COTS down to the threshold, which means there was 2.5 times as much time for COTS to consume coral before they were removed. So you lose much more coral under the pre-IPM program. They had a lower, roughly 2.5 times less likely to return to a site that needed to control as the IPM program, and roughly half the probability of achieving the threshold as the IPM program. They achieved lower reductions when densities were above 3 at the beginning, were above 3 hectares, and overall, across whether they achieved the threshold or not, the final densities in the pre-IPM program was roughly 4 times the density that with the threshold density, whereas the IPM density was below the threshold. They brought 53% of their sites to below the threshold versus 88% of the sites in the IPM program, and they achieved their objectives at exactly 0% of 102 reefs, whereas the IPM program achieved it at about 89% of 103 reefs. So all up, the IPM program is far more effective at achieving the harder objectives, the larger scale objectives, and what I would say are the ecologically meaningful objectives. Effectively, the pre-IPM program was a really effective way of killing COTS. The IPM turns that effective way of effective manual control into an effective and efficient means of achieving your management objectives at site, reef, and larger spatial scales. And the question really then becomes, well, how far can we scale this program up? So what might we achieve with the IPM program in the face of a new COTS outbreak? And I'm going to suggest that perhaps we could actually, given that sort of information, we might be able to actually reduce the magnitude of a future outbreak and modify its spread. But that's really going to be a function of 4 things: how much and what type of management effort we deploy, when we deploy it, where we deploy it, and the environmental constraints on that. So I'll just briefly walk you through those things. I'm going to talk about the potential of the program, and in doing so, I'm going to assume that we have a similar level of investment, 5 dedicated vessels, professional divers, and we're using manual control. I'm also going to assume, however, that we are going to invest far more effort into monitoring. We currently use manta tows for this current and for monitoring at the moment. It's fit for the purpose we use it for, but in the context of a new outbreak, we actually need to have better monitoring tools. And so we're going to need to invest in some of the new glider technologies that are coming through, which will allow us to do far more rapid, comprehensive and broad scale monitoring, will provide far better data, far greater accuracy and precision in the data, and allow us to address a whole range, not just COTS densities, but coral cover and reef conditions. And so yes, so I'm going to assume in this that we are going to be able to use those new monitoring technologies. But just to give you some idea of the scale of monitoring, of management that, or COTS control that we could expect to achieve, I'm going to just want to show you some data on how the average performance of the vessels under the IPM program. Each vessel has on average visited 23.5 reefs. They've towed roughly 1,000 kilometres around those reefs. They've conducted culls at 12 of those reefs. The remaining 11.5 reefs would have been assessed as not requiring culls. And they've reduced densities to below the threshold on nearly all of those 12 reefs. They've culled very large areas, as I said, about 1,000 they've culled about 1,000 hectares, and about 3/4 of that as areas where they've brought it to below the threshold. Now, if we can then extrapolate that potential across a period of 4 years and 5 boats, and across 8 years and 5 boats. And we're beginning to achieve large numbers, management at large numbers of reefs and at very large spatial scales. And I'll indicate now why those two time periods are really important by thinking about, I'll talk to you about that in a second. I'll come back to that. So we have capacity that can be scaled up over time to very large areas. When should we be deploying that? Well, our experience from invasive species and pest species management is in all sorts of terrestrial and marine areas is that you have to act as soon as you possibly can if you want success. Our current control methods target adults, and so we need to identify and act on adults at the very earliest stage in the outbreak cycle. So here you can see a timeline of outbreak cycle. We have an inter-outbreak population which produces the condition or responds to conditions and starts to produce mass spawning events, which allows the establishment of a high recruitment of high numbers of adults, and that turns a primary outbreak into a spreading secondary outbreak. Now, on the GBR, our history is that we implement our management here at the end of this part of the outbreak cycle, when we already have a spreading outbreak. But the first time we have adults available to cull is actually here during the inter-outbreak period. And this is when we might start to see small increases in the density of adults, or we might start to see spawning aggregations of adults. And so this actually represents the first opportunity and the critical opportunity when we have the greatest chance of achieving success. So we need to be able to start management as soon as we see in this outbreak period. And it's worth noting that adults are available all through the outbreak cycle. And at each of these early phases, initiation and establishment, they are available to kill. And any management that we implement at this time frame will actually reduce those densities. So we should be investing early. So a key component of this is managing early. We must maintain our monitoring and control capability throughout the entire outbreak period. We can't pause as we've done in previous outbreaks. That's going to equal failure. And we need to improve our ability to detect changes in adult density, and that's going to require better monitoring tools. Where should we invest our management? Well, we have 4 outbreaks that have started in the initiation box, so we might guess that that's where it's going to start again. And our data suggests, from this outbreak, suggests that we've got about roughly a 4-year period where the outbreak will be resident in the initiation box, hence my 4-year extrapolation. But during that period, COTS can also be dispersing larval plumes outside of the initiation box, and we can get this information from Sven Utege's modelling on using eDNA. And that suggests that, and our data suggests there's an additional 4-year residency period in this combined dispersal and initiation box. So we have a decent time frame to respond to these animals. But what is convenient is that this is the initiation and dispersal boxes are also the areas where our management capacity is best matches the scale of the GBR. It's the area with the fewest reefs and the smallest reefs. So this area needs to be the focus of our monitoring and control efforts. It can't be the only only focus, but it needs to be a dominant focus. Excuse me, I have a helicopter hovering overhead. So do we actually have the capacity to manage at these scales? What I've done here is looked at the number of reefs, the area of reefs, and the perimeter of reefs in the initiation box and the dispersal boxes and combined. And you can see we have, when you combine those areas, we have roughly 605 reefs that we're dealing with. It's about 671,000 hectares and about 6,000 cumulative kilometres of reef area. In the next two boxes on the right, I have from the IPM program, in the average year, the 5 vessels worked on 117 reefs. These reefs had a mapped area of 338,000 hectares and a perimeter of 4,852 kilometres. If we then extrapolate that out over the 4-year residency period for the initiation box, we can see that actually our control is beginning to look like it has, its capacity is reasonably well balanced with the task at hand. Now these, this is a really simple direct comparison. So we have to be careful about this. There's a whole range of assumptions that can go wrong. I think the take-home message from this is that the scale of the problem that we face and the scale of the capacity of the IPM program are not completely mismatched. And if we're careful about how we deploy our resources, and then we actually stand a chance of significantly influencing the trajectory of the next outbreak. Am I saying we can control or stop the next outbreak? Look, I think I need to be emphatic. I'm not saying that. There are a whole range of reasons why that and the next outbreak even could escape us, even under the most perfect circumstances. But I think that we can be confident that we stand a good chance of really significantly reducing the magnitude of an outbreak and influencing its pattern of spread. But to do that, we have to maintain our control capacity throughout the entire outbreak cycle. We have to improve our monitoring, and we need to improve some of our control activities, for example, how we manage deep water, etc. I think we're at a point where program objective now can evolve to reducing the outbreak magnitude of an outbreak and minimizing its spread at a GBR scale. That, I think, is a significant improvement over the original program. And I think what we can say from that then is that the IPM program really has provided a solid foundation for COTS control on the GBR going forward. As I said earlier, it's turned a method for killing COTS into a means for controlling COTS outbreaks at sites, reefs, regions, and aspirationally at the scale of the GBR. It's not perfect, but it's designed to be adaptive and is a good springboard for the future work of the program. Really have to emphasize though, we cannot stop control. Success is critically required that we maintain investment throughout the outbreak cycle. And we can see, yeah, that's going to be costly, but it's, we really need to look at the scale of that investment to the scale of the asset that we're trying to protect. And I think suddenly the cost becomes pretty small. So that's a wrap for me.